Flight is the main mode of locomotion used by most of the world's bird species. Flight assists birds while feeding, breeding, avoiding predators, and migrating. This article discusses the mechanics of bird flight, with emphasis on the varied forms of birds' wings. The specifics of hovering, takeoff and landing are also examined. Additional adaptations of birds' bodies relating to the flying ability are covered. Finally, theories on the evolution of bird flight are discussed. Basic mechanics of bird flight. Lift and drag. The fundamentals of bird flight are similar to those of aircraft, in which the aerodynamic forces sustaining flight are lift and drag. Lift force is produced by the action of airflow on the wing, which is an airfoil. The airfoil is shaped such that the air provides a net upward force on the wing, while the movement of air is directed downward. Additional net lift may come from airflow around the bird's body in some species, especially during intermittent flight while the wings are folded or semi-folded. Aerodynamic drag is the force opposite to the direction of motion, and hence the source of energy loss in flight. The drag force can be separated into two portions: lift-induced drag, which is inherent in the wing, and parasitic drag, including skin friction drag from the friction of air and body surfaces, and form drag from the bird's frontal area. The streamlining of bird's body and wings reduces these forces. Flapping flight. When a bird flaps, as opposed to gliding, its wings continue to develop lift as before, but the lift is rotated forward to provide thrust, which counteracts drag and increases its speed, which has the effect of also increasing lift to counteract its weight, allowing it to maintain height at a climb. Flapping involves two stages: the downstroke, which provides the majority of the thrust, and the upstroke, which can also provide some thrust. At each upstroke, the wing is slightly folded inwards to reduce the energetic cost of flapping wing flight. Birds change the angle of attack continuously within a flap, as well as with speed. Gliding flight. When in gliding flight, the upward aerodynamic force on both birds and gliders is equal to the weight. In gliding flight, no propulsion is used. The energy to counteract the energy lost due to aerodynamic drag is either taken from the potential energy of the bird, resulting in a descending flight, or is replaced by rising air currents referred to as soaring flight. Wing. The bird's forelimbs are the key to flight. Each wing has a central vein to hit the wind, composed of three limb bones: the humerus, ulna and radius. The hand, or manus, which ancestrally was composed of 5 digits, is reduced to 3 digits, which serves as an anchor for the primaries. One of two groups of flight feathers responsible for the wing's airfoil shape. The other set of flight feathers behind the carpal joint on the ulna are called the secondaries. The remaining feathers on the wing are known as covers, of which there are 3 sets. The wing sometimes has vestigial claws. In most species these are lost by the time the bird is adult, but claws are retained into adulthood by the secretary bird, screamers, finfoots, ostriches, several swifts and numerous others, as a local trait in a few specimens. Albatrosses have locking mechanisms in the wing joints that reduce the strain on the muscles during soaring flight. Female birds exposed to predators during ovulation produce chicks which grow the wings faster than chicks produced by predator-free females. The wings are also longer. Both adaptations may make them better at avoiding avian predators. Wing shape and flight. The shape of the wing is important in determining the flight capabilities of a bird. Different shapes correspond to different trade-offs between advantages such as speed, low energy use, and maneuverability. Two important parameters are the aspect ratio and wing loading. Aspect ratio is the ratio of wingspan to the mean of its chord. Wing loading is the ratio of weight to wing area. Most kinds of bird wing can be grouped into 4 types, with some falling between 2 of these types. These types of wings are elliptical wings, high-speed wings, high aspect ratio wings, and soaring wings with slots. Elliptical wings are short and rounded, having a low aspect ratio, allowing for tight maneuvering in confined spaces such as might be found in dense vegetation. As such, they are common in forest raptors and many passerines, particularly non-migratory ones. They are also common in species that use a rapid takeoff to evade predators, such as pheasants and partridges. High-speed wings are short, pointed wings that, when combined with the heavy wing loading and rapid wing beats, provide an energetically expensive high speed. This type of flight is used by the bird with the fastest wing speed, the peregrine falcon, as well as by most of the ducks. The same wing shape is used by the auks for a different purpose. Auks use the wings to fly underwater. The peregrine falcon has the highest recorded dive speed of 242 miles per hour. The fastest straight-powered flight is the spine-tailed swift at 105 miles per hour. High aspect ratio wings, which usually have low wing loading and are far longer than their wide, are used for slower flight. This may take the form of almost hovering or in soaring and gliding flight, particularly the dynamic soaring used by seabirds, which takes advantage of wind speed variation at different altitudes above ocean waves to provide lift. Low-speed flight is also important for birds that plunge dive for fish. Soaring wings with deep slots. These wings are favored by larger species of inland birds, such as eagles, vultures, pelicans, and storks. The slots at the end of the wings, between the primaries, reduce the induced drag and wingtip vortices by capturing the energy in air flowing from the lower to upper wing surface at the tips, whilst the shorter size of the wings aids in takeoff. Bounding flight. Small birds often fly long distances using a technique in which short bursts of flapping are alternated with intervals in which the wings are folded against the body. This is a flight pattern known as bounding or flap-bounding flight. During the period in which the wings are folded, the bird's trajectory is primarily ballistic with a small amount of body lift. The flight pattern is believed to decrease the energy required by reducing the aerodynamic drag during the ballistic part of the trajectory, and to increase the efficiency of muscle use. Hovering. Several bird species, including one family, use hovering. True hovering by generating lift through flapping alone rather than by passage through the air demands a lot of energy. This confines the ability to smaller birds. The largest bird able to truly hover is the pied kingfisher, although larger birds can hover for short periods of time. Larger birds that hover for prolonged periods do so by flying into a headwind, allowing them to remain stationary relative to the ground or water. Kestrels, terns, and even hawks use this wind hovering. Most birds that hover have high aspect ratio wings that are suited to low-speed flying. One major exception to this are the hummingbirds, which are the most accomplished hoverers of all the birds. Hummingbird flight is different from other bird flight in that the wing is extended throughout the whole stroke, the stroke being a symmetrical figure of 8, with the wing producing lift on both the up and down stroke. Some hummingbirds can beat the wings 52 times a second, though others do so less frequently. Takeoff and landing. Takeoff is one of the most energetically demanding aspects of flight, as the bird must generate enough airflow across the wing to create lift. Small birds do this with a simple upward jump. that doesn't work for larger birds, which must take a run up to generate sufficient airflow. Large birds take off by facing into the wind, or, if they can, by perching on a branch or cliff so they can just drop off into the air. Landing is also a problem for large birds with high wing loads. This problem is dealt with in some species by aiming for a point below the intended landing area, then pulling up beforehand. If timed correctly, the airspeed once the target is reached is virtually nil. Landing on water is simpler, and the larger waterfowl species prefer to do so whenever possible, landing into wind and using the feet as skids to lose height rapidly prior to landing. Some large birds such as geese indulge in a rapid alternating series of side slips, or even briefly turning upside down in a maneuver termed as whiffling. Coordinated formation flight. A wide variety of birds fly together in a symmetric V-shaped or AJ-shaped coordinated formation, also referred to as an echelon, especially during long-distance flight migration. This pattern of formation flying is resorted to so as to save energy and improve the aerodynamic efficiency of birds. The birds flying at the tips and at the front interchange positions in a timely cyclical fashion to spread flight fatigue equally among the flock members. The wingtips of the leading bird in an echelon create a pair of opposite rotating line vortices. The vortices trailing a bird create an underwash which creates an induced drag for the bird, creating it. At the same time, these vortices create an upwash which can aid the flight of any bird following. In a 1970 study, the authors claimed that each bird in a V formation of 25 members can achieve a reduction of induced drag and as a result increase the range by 71%. Studies of wall-drap ibis show that birds spatially coordinate the phase of wing flapping and show wingtip path coherence when flying in V positions, thus enabling them to maximally utilize the available energy of upwash over the entire flap cycle. In contrast, birds flying in a stream immediately one behind another do not have wingtip coherence in the flight pattern, and the flapping is out of phase, as compared to birds flying in V patterns, so as to avoid the detrimental effects of the downwash due to the leading bird's flight. Adaptations for flight. The most obvious adaptation to flight is the wing, but because flight is so energetically demanding, birds have evolved several other adaptations to improve efficiency when flying. Birds' bodies are streamlined to help overcome air resistance. Also, the bird's skeleton is hollow to reduce weight, and many unnecessary bones have been lost, along with the toothed jaw of early birds, which has been replaced with a lightweight beak. The skeleton's breastbone has also adapted into a large keel, suitable for the attachment of large, powerful flight muscles. The veins of each feather have hooklets called barbules that zip the veins of individual feathers together, giving the feathers the strength needed to hold the airfoil. The barbules maintain the shape and function of the feather. Each feather has a major side and a minor side, meaning that the shaft or arches does not run down the center of the feather. Rather, it runs longitudinally of center, with the lesser or minor side to the front and the greater or major side to the rear of the feather. This feather anatomy, during flight and flapping of the wings, causes a rotation of the feather in its follicle. The rotation occurs in the up motion of the wing. The greater side points down, letting air slip through the wing. This essentially breaks the integrity of the wing, allowing for a much easier movement in the up direction. The integrity of the wing is re-established in the down movement, which allows for part of the lift inherent in bird wings. This function is most important in taking off or achieving lift at very low or slow speeds, where the bird is reaching up and grabbing air and pulling itself up. At high speeds, the airfoil function of the wing provides most of the lift needed to stay in flight. The larger amounts of energy required for flight have led to the evolution of a unidirectional pulmonary system to provide the large quantities of oxygen required for the high respiratory rates. This high metabolic rate produces large quantities of radicals in the cells that can damage DNA and lead to tumors. Birds, however, do not suffer from an otherwise expected shortened lifespan, as the cells have evolved a more efficient antioxidant system than those found in other animals. Evolution of bird flight. Most paleontologists agree that birds evolved from small theropod dinosaurs, but the origin of bird flight is one of the oldest and most hotly contested debates in paleontology. The four main hypotheses are: for the trees down, that birds' ancestors first glided down from trees and then acquired other modifications that enable true bird flight; from the ground up, that birds' ancestors were small, fast predatory dinosaurs in which feathers developed for other reasons and then evolved further to provide first lift and then true bird flight. Wing-assisted incline running, a version of from the ground up, in which birds' wings originated from forelimb modifications that provided downforce, enabling the protobirds to run up extremely steep slopes such as the trunks of trees. Hansing pro avis, which posits that flight evolved by modification from arboreal ambush tactics. There has also been debate about whether the earliest known bird, Archaeopteryx, could fly. It appears that Archaeopteryx had the brain structures and inner ear balance senses that birds used to control their flight. Archaeopteryx also had a wing feather arrangement like that of modern birds and similarly asymmetrical flight feathers on its wings and tail. But Archaeopteryx lacked the shoulder mechanism by which modern birds' wings produce swift, powerful upstrokes. This may mean that it and other early birds were incapable of flapping flight and could only glide. The presence of most fossils in marine sediments in habitats devoid of vegetation has led to the hypothesis that they may have used the wings as aids to run across the water surface in the manner of the basilisk lizards. For the trees down, this was the earliest hypothesis, encouraged by the examples of gliding vertebrates such as flying squirrels. It suggests that proto-birds like Archaeopteryx used the claws to clamber up trees and glided off from the tops. Some recent research undermines the trees down hypothesis by suggesting that the earliest birds and their immediate ancestors did not climb trees. Modern birds that forage in trees have much more curved toe claws than those that forage on the ground. The toe claws of Mesozoic birds and of closely related non-avian theropod dinosaurs are like those of modern ground foraging birds. For the ground-up, feathers are very common in coelurosaurid dinosaurs. Modern birds are classified as coelurosaurs by nearly all paleontologists, though not by a few ornithologists. The original functions of feathers may have included thermal insulation and competitive displays. The most common version of the from the ground up hypothesis argues that birds' ancestors were small ground-running predators that used their forelimbs for balance while pursuing prey, and that the forelimbs and feathers later evolved in ways that provided gliding and then powered flight. Another ground-upwards theory argues the evolution of flight was initially driven by competitive displays and fighting. Displays required longer feathers and longer, stronger forelimbs. Many modern birds use the wings as weapons, and downward blows have a similar action to that of flapping flight. Many of the Archaeopteryx fossils come from marine marine sediments, and it has been suggested that wings may have helped the birds run over water in the manner of the Jesus Christ lizard. Most recent attacks on the from-the-ground-up hypothesis attempt to refute its assumption that birds are modified coelurosaurid dinosaurs. The strongest attacks are based on embryological analyses, which conclude that birds' wings are formed from digits 2, 3 and 4, but the hands of coelurosaurs are formed by digits 1, 2 and 3. However, these embryological analyses were immediately challenged on the embryological grounds that the hand often develops differently in clades that have lost some digits in the course of their evolution, and therefore birds' hands to develop from digits 1, 2 and 3. Wing-assisted incline running. The wing-assisted incline running hypothesis was prompted by observation of young chukar chicks, and proposes that wings developed their aerodynamic functions as a result of the need to run quickly up very steep slopes such as tree trunks, for example to escape from predators. Note that in this scenario birds need downforce to give the feet increased grip, but early birds, including Archaeopteryx, lacked the shoulder mechanism by which modern birds' wings produce swift, powerful upstrokes, since the downforce on which wear depends is generated by upstrokes. It seems that early birds were incapable of wear-enhancing Pro-Avis model. The Pro-Avis theory was first proposed by Garner, Taylor, and Thomas in 1999. We propose that birds evolved from predators that specialized in ambush from elevated sites, using the raptorial hind limbs in a leaping attack. Drag-based, and later lift-based, mechanisms evolved under selection for improved control of body position and locomotion during the aerial part of the attack. Selection for enhanced lift-based control led to improved lift coefficients, incidentally turning a pounce into a swoop as lift production increased. Selection for greater swooping range would finally lead to the origin of true flight. The authors believed that this theory had four main virtues. It predicts the observed sequence of character acquisition in avian evolution. It predicts an Archaeopteryx-like animal with a skeleton more or less identical to terrestrial theropods, with few adaptations to flapping, but very advanced aerodynamic asymmetrical feathers. It explains that primitive pantsers could coexist with more advanced flyers since they did not compete for flying niches. It explains that the evolution of elongated cheese-bearing feathers began with simple forms that produced a benefit by increasing drag. Later, more refined feather shapes could begin to also provide lift. Uses and loss of flight in modern birds. Birds use flight to obtain prey on the wing, for foraging, to commute to feeding grounds, and to migrate between the seasons. It is also used by some species to display during the breeding season and to reach safe isolated places for nesting. Flight is more energetically expensive in larger birds, and many of the largest species fly by soaring and gliding as much as possible. Many physiological adaptations have evolved that make flight more efficient. Birds that settle on isolated oceanic islands that lack ground-based predators often lose the ability to fly. This illustrates both flight's importance in avoiding predators and its extreme demand for energy.